Correlation versus causation. When using statistics in a debate, a common fallacy people commit is to confuse correlation with causation. Let's look at these two terms and see how they are and aren't related. A correlation is when two sets of data change in value simultaneously in such a way that the general trend of one data set also describes the trend of the other data set. For example, smoking is correlated with the occurrence of lung cancer. As the number of cigarettes a person smokes increases, the likelihood of developing lung cancer also increases. Those two datasets move in relation to each other. Despite this correlation, it doesn't necessarily describe any individual person. In other words, just because a person smokes, that doesn't necessarily mean that person will develop lung cancer. But based on this correlation, we know that the person is more likely to develop lung cancer, because the general trend of smoking is correlated with the general trend of lung cancer occurrence. In other words, correlations describe trends, not individuals. Now let's look at the next term, causation. When one event occurs as a result of another event, there is what is known as a causal relationship between those two events. A simple example is if I am holding a ball in my hand and I let go. The ball falls to the ground. The pull of gravity has a causal relationship with the ball falling to the ground. The fallacy is when someone assumes that because there is a correlation, there must be a causation between two events. But that's not the case. It is possible for two things to be correlated without one causing the other, and can result in the fallacy of confusing correlation with causation. This fallacy can take many forms, depending on why the apparent relationship exists. The first form is known as reverse causation, which is when the cause and effect relationship are backwards. In other words, instead of event A causing event B, it is actually event B that causes event A. Here's an example that commits the reverse causation fallacy. Whenever it gets dark outside, people have their car headlights on. Therefore, car headlights must be what causes the sun to go down. This, of course, is backwards. It is true that there is a correlation between the sun going down and headlights coming on, but that doesn't mean the car headlights cause the sun to go down. Instead, the sun going down is the reason the headlights come on. Just because there is a correlation between headlights coming on and the sun going down, it is incorrect to conclude that the headlights caused the sun to set. Now, in this example, there was a cause and effect relationship between the events. It was just backwards. But in many cases, there won't be any cause and effect relationship at all, even if there is a correlation. One example of this is the common cause fallacy, in which event A and event B appeared to be related, but only because a third event, C, caused both of them. Here's an example of this fallacy. The months when people eat the most ice cream are also the months when the most drowning deaths occur. Therefore, ice cream must cause people to drown. Someone who is confusing correlation with causation might see this correlation and conclude that ice cream causes people to drown. This obviously makes no sense. Instead, it is simply the case that the hot weather is what sends people to the pool and gets them to eat ice cream. There may appear to be a correlation between the events, but that is only because they have the same root cause, the hot weather. Despite the correlation, there is no causal relationship between ice cream and drowning. In addition to the reverse causation and common cause fallacies, another fallacy is to assume that a causal relationship exists between two datasets when they are only correlated out of mere coincidence. Just because two sets of data have a correlation, it cannot necessarily be concluded that there is a cause and effect relationship between those sets of data. Typically, correlations are just used as a preliminary evidence to see if it is worth looking at a relationship more closely. Then, if a correlation is found, more controlled studies can be done to see if there is a causal relationship. This recording is by learnabit.com. Learn about science in 10 minutes or less with free audio lectures from Learnabit. That's LERNABIT.com.